This presentation is titled Graph Neat Examples in Raku, Set 3. My name is Anton Antonov. Today is November 28, 2024. I have prepared two sets of examples, nested graphs and file system graphs. The neat examples in general are defined as concise or straightforward code that produce compelling visual textual outputs. I'm going to be demonstrating the functionalities of the Raku package graph. The graphs are going to be visualized using JavaScript or D3.js. This is a JavaScript library D3.js, and D3.js is being utilized in Raku through JavaScript D3. Graph itself, the package graph itself, knows how to produce SVG images via the framework called GraphVis, which is an old framework for specifying and displaying graphs. All right, so nested graphs, basic examples are here. So this should demonstrate why they're called nested graphs. So we start with a certain value, say x, and then I apply a certain function to it and so forth, right? So you can see the applications of f are nested, so to speak. And so the way these nested graphs are specified here is we use the graph nested class. We make this with the new signature. We have the first argument to be a function, the second argument to be an initial value, and then the number of times we apply it. And we can see this for 2, being squared, and it's squared again, and with x being nested in this way to produce this symbolic representation. All right, same example, but with two functions. I'm using the functions f and g. Again, I start with x, I apply this function, the first argument, 3 times, and we can see we get this kind of nestings. And I can display this graph so with JavaScript, D3.js, as I mentioned. And so here, this is with the SVG GraphVis functionalities using the method dot. So if I show you what this is here, this is SVG code, right? And here this is JavaScript code. So if I evaluate this is JavaScript code, which is being rendered readily in this Jupyter notebook. All right, mod graph is somewhat probably more complicated, but produces more complicated graph. The reason for this is that we take whatever is the vertex value, say 3, and I square it and I add 1 to it, and then I take the mod. So 9, if it is squared, is 81, plus 1, 82, mod 10 is 2. So we get this directed graph. So you can see that I have used all of the integers from 0 to 9. This is what is specified here. By default, only one nesting is being applied. Okay, range graph is somewhat maybe more convenient to demonstrate what's going on. So if I make only one step in this nesting, what is going to happen? So I start with this value 9, and I intentionally used a string here, and this here is the allomorph application of it, or allomorph functionalities of Raku applied to it. And so here we can see that from 9 we produce this result from 0 to 8. And so if I do a second application, nested application, then we're going to produce a much more comprehensive, larger graph. And we can see that if this graph is made undirected, it is a directed graph, but if it is made undirected, then it is a complete graph. And also, we can compute the in degree and out degree of each vertex. We can see that no other vertices make edges that go into 9. So all edges of 9, they go out. And similarly to 0, it's the other way around, right? And so we can see here this with the methods vertex in degree and vertex out degree. If we use this adverb pairs or the abbreviation P, we get only the corresponding degrees, and we can also get this these pairs corresponding to the degrees. I can visualize this using D3.js. This is not necessarily a very nice plot. It's just it's a very busy graph. And it's hard to display better, in my opinion, when using this rendering. Okay, the file system graphs. So I'm going to use a package recently created or recently submitted to Raku line package called puffs, and I'm going to take the files from a directory with mathematical notebooks about Raku, which I have been using to do Raku. This is before I started using Jupyter framework for anything Raku related. So here I'm going to visualize the graph. So we get this graph here, and what is happening. So from the paths, I split them in some way in order to get the individual directories and the files themselves. Then I create edges from the say root directory to the subdirectories, from the subdirectories to their own subdirectories, and so forth until we reach the actual files, right? And you can see I have 186 files and corresponding edges and so forth. So here I'm using the so-called circular embedding for this graph. And if I want to show what these are file names, I'm going to remove that specification so we can see these are file names. It's like CSV files, zip files, NB, these are mathematical notebooks, and so forth. All right, so let's do the same thing, but using the Raku doc files. This is from the Raku doc repository. I cloned it today from GitHub, and probably the target audience of this presentation is going to be more interested in that. So here I'm producing this graph, and I'm plotting it with JavaScript plot using the free GS. And so you can see that I'm using the force display here, and I have squashed the graph a little bit from the y direction in order to produce this. Let me show the actual names, which probably the Raku practitioners are going to recognize. So we have the comp unit, we have hash Raku doc, and etc. Right. So if I try to move any of those to get more eligible, I should have made this nodes easier to pick and select. All right. So if I put here none, we're going to get the original plot, and this is my last neat examples here. All right. Thank you.